Hi, Chris Good here, and this is part 2 of our second video lecture, which is on the repeated measures t-test. And we're going to stay with our example of looking for the effects of ginkgo on people's memory compared to a placebo, but we're not going to use the data that appear in this graph, so don't worry about these data right now. Before we get started, I want to go back to the t-test you already know how to do, which is the independent measures t-test. Here, t is equal to the difference between two sample means. Those are the means from the samples made up of different people in one group experiencing one treatment and another group of different people in a second group that is experiencing a different treatment. We subtract from that difference between these two sample means a hypothetical population mean difference score. So we have two sample means, we're looking at their difference, we measure those, and we have two population means, and we hypothesize that the difference between them is 0. That's our null hypothesis, and that really means that our treatment didn't do anything, which is a little counterintuitive, because we wouldn't be doing this if we didn't think that our treatment did do something. But we have to make this assumption in order to calculate t, otherwise we don't have anything to put in this term in the numerator. So what this allows us to do is to use the value for t we calculate to guide us in a decision about this null hypothesis assumption. We're either going to reject it if the difference between the two sample means is so far apart that it's really unlikely we would find them when the null is true, or we'll stick with this idea if it's fairly likely that we would randomly get these two sample means that are fairly close together when the null is definitely true. The tricky part is you'll never know for sure whether the null was actually true or not, and so this is only a guide to making that decision. But if you want to delve deeper into that, please do go see the video on t and p, which is our measure of probability, and the null hypothesis, and I hope that that will clear things up. Okay, one last look at the independent measures t-test. Difference between two sample means. The repeated measures t-test is very similar to it. Instead of a difference between two sample means, we only have one sample mean. But that mean is the mean of a sample of different scores, and I'm going to show you what those are in just a moment. We're going to subtract from that sample mean difference score a hypothetical population mean difference score, and I bet you already have an idea as to the value we'll attach to that. We'll divide that by an estimated standard error of that mean difference score, and before we go any further, let's just talk about what difference scores are. In a repeated measures design, you already know from watching part 1 of this lecture that each participant, experiences both conditions of the study. So here in this table we see participant number 1 scored a 2 on the memory test while taking the placebo and a 4 on the same test while taking ginkgo. Now, I'll assure you right now that the design was appropriately counterbalanced, and so there's no chance of carryover effects or progressive error affecting the outcome of the study at all. And we can see that this participant number 1, who scored 2 on placebo and a 4 while taking ginkgo, has a different score of 2. We got that simply by subtracting the placebo score from the ginkgo score. We do that for each individual, and we come up with a sample of difference scores, and we have one for each participant. We could calculate the average of these different scores, and that's what the mean difference score is. That m sub d that we see here in the numerator of the repeated measures t is simply the sum of the difference scores divided by the number of different scores. It's their average. So let's do that. We can even do it in our heads. 2 plus 4 is 6. 6 divided by how many different scores? We have 5. So that's 1.2 is our mean difference score, or average difference score for this sample. Well, we're almost there. We got that 1.2 in the numerator minus the population mean difference score. Well, where do we get the hypothetical population mean difference score? Well, we get it from the null hypothesis. The null hypothesis means that your treatment doesn't do anything. And if it really doesn't, then some people sometimes are going to have a higher score on ginkgo, some people sometimes are going to have a higher score on placebo, but on average, they'll be around the same, and so the average difference score for an entire population, when ginkgo doesn't do anything, is going to be, you guessed it, 0. So for the mu sub d in the numerator of the t equation, we'll put in 0. So 1.2 minus 0, we're practically done. Well, we're going to divide that mean difference score by the estimated standard error of the mean difference score. And very much like the independent samples t-test, it's the square root of the variance for the difference scores divided by the number of the difference scores. That variance is the sum of squares for the different scores divided by the degrees of freedom for the different scores, or the number of different scores minus 1. How do we get the sum of the squares for the different score? Well, we could do it the old-fashioned way by subtracting the mean difference score that we just calculated, 1.2, from each one of our different scores, or we could use the computational formula, and that's what I'm going to use in the example. All right, for these data, right, to do our repeated measures t-test, we're going to do the same 4 things we do for every t-test. First, we're going to state the null hypothesis. And the null here is that our treatment did nothing, or that the population mean difference score will always be 0. Okay? That's how we complete the numerator of the t. Step 2, select alpha and determine the critical value for t. Well, to determine the critical value, we will need the degrees of freedom. That's the number of, remember, it's the number of different scores. We're not testing the total number of scores that we have. We're testing the number of different scores, which is equal to the number of participants we have, which is 5. So 5 minus 1 is 4, and those are the degrees of freedom that we'll use in the t-table to look up our critical value. Now, you'll notice that if we had done this as an independent groups t-test, we'd have double this degrees of freedom. We'd have 4 plus 4, because we'd be using the number of scores that we have, minus 1, plus the number of scores that we have in the other group, minus 1. So 4 and 4 is 8. And you'll see that the critical value for t that we use, when we do it as an independent measure study, are the critical value is actually lower or less extreme than the critical value that we have. So at first glance, it looks like it's easier to reject a null with an independent measures t-test, but it turns out that it's not, and I'll show you why in just a second. Anyway, with 2 tails, and I got this from the t-table, we get plus or minus 2.776 for degrees of freedom equal to 4 at an alpha of 0.05. That's step 2. Step 3, calculate t. Well, t, I'll skip to t down here. T is the difference between our sample mean difference score, which is 1.2, and the population mean difference score, which is 0. It's divided by the estimated standard error, the mean difference score, which is the square root of the variance over the number of different scores. The variance is the sum of squares, and so I have to start there. I'm going to use the computational formula here and sum the squared difference scores. So the first difference score is 2 squared is 4. Then it's just 1 plus 1 plus 1 plus 1. That's 8, right? Minus the square of the sum of the different scores. The sum of the different scores is 6. Squared is 36. You divide that by the number of scores that we have, right? Number of different scores, that's 5. So it's 8 minus 36 over 5, or 0.8 for our sum of the squared deviations of each different score from their mean. Plug that into the solve for the variance, and we get 0.8 over 4, which was our degrees of freedom. So we get 0.2 for the variance, and we'll just plug that in here to the estimated standard error of the mean difference score. That's S sub m sub d. As square root of 0.2 over 5, or the square root of 0.04, which is equal to 0.2. We'll use that in the denominator and find that t is equal to 6 here. 6 is way beyond plus 2.776, and then that'll help us make our decision to reject that null hypothesis, that the treatment does nothing. We'll reject that idea and conclude that this treatment significantly increases. It's not sufficient to say that the that the difference is significant. You need to say what that difference is. You need to tell me in your sentence what direction the effect goes in. And here, the treatment significantly increases participants' memory scores. I'll give the values there in APA format that we'll discuss in class. T with 4 degrees of freedom equals 6, and we know because we rejected the null that P is less than our alpha, less than 0.05. Here's a thought. What if we did this study as an independent measures study, and we didn't have different scores? What if we just ran an independent measures t-test on the same data? Well, we'd state our null, which is the difference between our two means, is 0, or two population means. Same alpha, but we get different critical values for t because, like I said before, the degrees of freedom change from 4 to 8. That means that the critical values are less extreme. It's plus or minus 2.306 instead of plus or minus 2.776, still with two tails. We pool our variance, and I won't walk you all the way through the calculations, but sum of squares for 1 is 10, sum of squares for 2 is 6.8. So that means the pooled variance is 2.1. Plug that in here to get our estimated standard error of the difference between these two means is 0.917. Look at the difference between the two sample means, and I got 4 for the placebo group, 5.2 for the ginkgo. Of course, 0 because of the null hypothesis for the difference between the two population means. Anyway, I get a t of negative 1.31. It's negative because I subtracted ginkgo from placebo instead of the other way around like we did for the different scores. And that's not beyond negative 2.306. And so we fail to reject. Oops, sorry, it says reject on the screen, but we actually failed to reject the null hypothesis. And we conclude we did not detect a significant effect of ginkgo on memory and report all the t as per APA style. Here p is greater than the alpha we selected because we failed. Again, that's incorrect there. The decision should be failed to reject the null or retain the null. And how could that be? Well, this is just to illustrate the power of this repeated measures design. And by power, I mean that in the statistical sense. It is more sensitive to detecting significant effects. Okay, so that is the repeated measures t-test. I will post an example of me solving a problem from the book before the end of the week. And please do check out the complimentary video that goes along with part 1, which is the Latin square video as well. And I'll see you guys in class.